Assalamu alaikum. I am Omar Farok from Kumbh University, Department of CSC. My ID is 120043. Today I am present on principal component analysis. So without further delay, let us start my presentation. Well, having too many features in data can cause problems like overfitting, slower computation, and lower accuracy. This is called curse of dimensionality. The explosion of feature combinations makes sampling harder in high-dimensional data and tasks clustering or classification more complex and slow. So, tackle this problem, we use feature engineering techniques such as feature selection, choosing the most important features, and feature extractions, creating a new feature from original ones. And the most important feature extractions method is dimensional reduction, and we widely used dimensional reduction technique is principal component analysis. Now we see how PCA work for dimensional reduction. Let's understand it working procedure step by step. In the first step, we standardize the data. It ensures that the each variable has a mean of 0 and a standard deviation of 1, and we calculate it z equal to x minus a mu by sigma, where mu is the mean of independent variable and sigma is the standard deviation. Well, in the second step, we find relationships. Calculate how features move together using a covariance matrix. Here, covariance matrix is the strength of joint variability between two or more variables, indicating how they change in relation in each other. We calculate covariance matrix by the formula covariance x1 x2 is equal to summation of I is equal to 1 when xii minus x bar x2I minus x2 bar by n minus 1. Well, in the third steps, we find magic direction. First principal component, the direction of maximum variance, and the second principal component, the next best directions, which is perpendicular to PCA1, and so on. These directions are calculated using eigenvectors and eigenmatrix, where eigenvectors met tools that find this exist and the importance is ranked by eigenvalues. How the variance each capture. Well, for a square matrix A, an eigenvector x and corresponding eigenvalues lambda, we represent the equations ax is equal to lambda x. When ax on x, it only stresses x by the scalar lambda. It can also be represented ax minus lambda x is equal to 0. If we take common x, a minus lambda I is equal to 0, where I is a identity matrix. The equation is only true for a non-inversible matrix, that is a minus lambda x is equal to 0. This is called the characteristics equation, and if we solve these equations, we find the lambda's values, that is eigenvalues, and for this lambda, we find corresponding eigenvectors from the equation x is equal to lambda x. Well, and now we see how this connect to PCA. In PCA, the covariance matrix C from step 2 X as matrix A, eigenvectors of C are the principal component and eigenvalues represent the variance captured by the principal component. In the last steps, we see pick the top directions and transformation data. Keep only the top 2 to 3 directions which captures actually 95% variance that project onto the project the direction to get a simplified lower dimensional version. Well, now let us understand again with help of visual image, where x-axis represent radius and y-axis represent area, represent two original features in the data set. Here the PCA1 represented and here the PCA2 represented. PCA1 is the most maximum variance and PCA2 is the remaining variance. which is perpendicular to PCA1. The variance along PCA1 is greater than PCA2, which means that PCA carries more useful information about the dataset. The data point here, blue dotted, are point projected on PCA1, effectively reducing the dataset from the dimensional, that is radius or area, to one direction, that is PCA1. Thank you all. This is my presentation. If you need query, please tell. Thank you all.